This video is about tangent planes and a linear approximation. If I give you a function depending on single variable, we know the graph is a curve. If I give you a point on the curve, say x0, y0, then you can talk about its tangent line. Okay, now if I give you a function depending on two variables, its graph this time is a surface. Is a surface, and I give you a point on the surface, say x0, y0, z0. Then obviously, or naturally, we don't talk about tangent line anymore. We're talking about what? Tangent plane, similarly, like that. Okay. This plane would touch this surface at that point, just one point. Just touch it. Okay. Now the question, how do we find equation for the tangent plane? We learned in the equation of line and equation of plane. Any plane can be written like this. I mean, any plane past the point x0, y0, z0 can be written like this. Y minus y0 plus c z minus z0 equal to 0. So any equation past that point, x0, y0, z0 can be written in this form. Okay, the question, we need to find a, b, and c. Now, if c is non-zero, we can solve for z minus z0 equal to d, say x minus x0 plus e y minus y0. My d here, you can think about is what? Is minus a over b, right? Okay. Similar, you can find e. Okay. Anyway, so any equation of line, any equation of the plane past the point x0, y0, z0 can be written in this form. So what we need to do, just find d and e, then we're done. We find the equation of the plane. Okay, how do we find the d and e? Now, go down here, this is point x0, y0. Okay. Now, let y equal to y0. Then this equation becomes to z minus z0 equal to d times x minus x0. What this equation means, y equal to x0 equal to y0 is like this. Remember, this is y equal to y0 give you a plane parallel with xz plane. Go up, will intersect your surface, get a curve like that. And also this y equal to y0 will intersect your tangent plane. Two plane intersection give you what? Give you a line. Okay. This line, in fact, is what? Tangent line to this curve. Okay. So we know the slope of this tangent line. Remember, that's what we learned in the previous section. That's exactly the partial f to respect to x. Evaluate at that point. Okay. So we can find a d. Remember, the meaning of a partial derivative with respect to x give you what? Slope of a tangent. For the curve, how do we get the curve? Intersect with your surface by y equal to y0. Okay. Similarly, we can find e there equal to partial f with respect to y at x naught, y naught. Therefore, we find the equation of a tangent plane is like this: fx, x naught, y naught, x minus x naught, plus fy evaluate this point, and y minus y naught. Remember, what is z0? Z naught is on the surface, really equal to what? Fx naught, y naught, right? It's not hard to see. Okay. Therefore, we can rewrite this one, z equal to z naught, which is fx naught, y naught, plus fx, x naught, y naught, x minus x naught, plus fy, x0, y0, and y minus y0. So what is this? This is the equation of the tangent plane, which we also called is a linear approximation, or say linearization. Okay, the right hand side of the equation on the box, we give a name. We say Lxy. Okay. Obviously, is a linear function of x and y. Okay, so to find the equation of the plane and to find the linearization, we'll say linear approximation is the same thing. Okay. Now, Lxy, which is a linear approximation for xy, will be very close to fxy if this point is close to x naught, y naught. Okay. This can be seen as a 1D case. Okay. Function depends on one variable. Let me show you what we mean by that. Now this is the point, right? You have a tangent line. This point is x naught, y naught. This tangent line really is linearization for the fx. This is the fx. So you got two functions. One is fx, another is Lx. This is x naught. If you pick your x far away from x naught, then this is the fx, this is the Lx. They're quite different. If you choose your x is very close to x naught, this is the fx, this is the Lx. They're very close to each other, right? If x close to x naught, then fx will close to Lx. That's why we call it a linear approximation. Okay. Okay, now let's look at the example. We want to find linearization. Linearization for the given function fxy here equal to x e to the xy at the point point 1, 0. Okay, now remember the formula is like this: fx naught, y naught, x minus x naught, plus fx, x naught y naught x minus x naught plus fy x naught y naught y minus y naught. Okay. This is a linearization for giving fxy and x naught y naught. For this specific problem, I give you fxy like that, and I give you x naught equal to 1, y naught equal to 0. So what do you need to do? Just find fx naught, y naught, and this one, and this three coefficients. Okay. So first of all, let's find fx naught, y naught, which is f1, 0, sorry. Now, go back to here, x equal to 1, y equal to 0. So 1 times e to the 0, give you 1. Okay. So next thing we need to find fx, evaluate 1, 0. So before we do that, we have to find this. Okay, this means we want to take a partial derivative with respect to x on fx, right? Now this one, you replace f here by the function you have. Okay, now we're taking partial derivative, so you treat y as a constant. Now, we have two functions, so we have to use the product rule. Take derivative of first one, fix second one change, give you 1 times e to the xy. Okay. Then plus, fix x, take derivative of second one, use the chain rule, give you e to the xy, then take derivative of xy. Treat y as a constant, so give you y. Then you have to find fx 1, 0. So the first one give you 1, second one give you 0. Because y there, y equal to 0. Then we have to find fy, xy. Okay, to find fy, that means you want to find the partial derivative of f respect to y. Replace your f by the given function. This one's easier because what? You treat x as a constant. So the first x is a constant, you put that out. Take derivative of the second one, give you e to the xy. Then take derivative of that respect to y, treat x as constant to give you this. Then you have to replace xy by 1, 0. When you talk about find the tangent plane or linearization, you have to tell me you want to do that at which point. Okay. So replace in the above equation, replace x by 1. 1 times y is 0, give you 1 times 1, so it give you 1. Therefore, your linearization Lxy equal to, just plug in, okay, fx naught y naught give you 1 plus also 1, right? So 1 times x minus 1, x naught is 1, plus 1 times y minus 0. Okay, so you can simplify that, give you 1 plus x minus 1, then plus y. So simply give you x plus y. Okay. Now we want to we really want to find this. F x is 1.1, y is minus 0.1. Okay. We want to find this number. Now, think about this. If you don't have a calculator, it's very hard for you to find this one. If you don't have a calculator, if you only can do addition, subtraction, multiplication, and division, it's very hard for you to find this one. Now, however, this one can be approximated by 1.1 and the minus 0.1, right? This one's easy to find. You just plug in there, x is 1.1 plus y, which is minus 0.1. They give you 1. Okay. But this one is not exactly what is. If you use your calculator, it's not hard to find. This one gives you 0.985 something. Obviously, 1 is a good approximation to that. Y, this time, L 1.1 is a linear approximation give you a good approximation. That's because of what? 1.1 and the negative 0.1 is what? Very close to the point 1 and 0. Okay, another thing we need to learn is like we call the total differential. Okay, total differential has been defined this way: partial z respect to x dx plus partial z respect to y dy. Remember, for the single variable function, we define something called a differential, like this way: dy dx dx. Okay. Or you can write this f prime of x dx. We call it dy the differential. Okay. Now, similarly, for the function depending on two variables, we can naturally to have this. Okay, if dy equal to 0, we can say what? This implies f prime of x is 0. Means what? Your y equal to fx is what? Constant. Okay. Now look at it here. If I have function partial z respect to x equal to 0, this does not imply z is a constant. Okay, this only say what? Z only depends on x. Then partial z respect to y equal to 0. That implies your z only depends on y. Okay. However, if your total differential equal to 0, that implies partial f respect to x and the partial f respect to y, they're both 0. That implies, f and z same thing, okay, is constant.